In October 2015, in a quiet room in London, a professional Go player sat across from an opponent that didn't eat, didn't sleep, and didn't even breathe. It lived in racks of computers humming in the background. On the board, 19 by 19 lines, black and white stones, a game so subtle and so vast that for decades experts said, no computer will touch top human level for at least another 10 years. And yet, over 5 official games, this machine didn't just hold its own. It won. 5-0. That machine was AlphaGo. Today, we're going to unpack the science behind the breakthrough paper, Mastering the Game of Go with Deep Neural Networks and Tree Search. The work that took Go from AI's final boss to solved enough that humans can't keep up. We're going to go inside AlphaGo's brain, how it sees the board, how it chooses moves, how it trains itself with millions of games of self-play, and how it combines deep learning with search to play Go at a professional level. Before we dive into this beautiful blend of math, code, and strategy, hit like, smash that subscribe button, and ring the bell so you don't miss future deep dives into the papers that changed AI forever. And if you're already thinking of a favorite AI paper you want broken down, keep it in mind for the comments at the end. Let's start with why Go was such a big deal in the first place. Games like checkers and chess have long been conquered by machines. Programs like Deep Blue beat world champions by searching gigantic trees of possibilities. In a typical chess position, there are about 35 legal moves, and a game might go 80 moves deep. That's astronomically large, but with clever pruning and good heuristics, computers can brute force a surprising fraction of that tree. Go laughs at that approach. On a 19 by 19 Go board, a typical position has around 250 legal moves. A full game can last 150 moves or more. Multiply that out, and the search space makes chess look tiny. Just enumerating possible games is hopeless. But that's only half the problem. The other half is evaluation. In chess, you can estimate material plus position with hand-designed rules. Rooks are worth 5, queens 9, pawns 1, plus some positional tweaks. In Go, the value of a position, who's actually winning, is a mysterious swirl of influence, territory, and future potential. For decades, people tried to design evaluation functions and largely failed. Computers played like weak amateurs. Earlier Go engines turned to Monte Carlo tree search, or MCTS. Instead of trying to be smart everywhere, they would simulate thousands of random playouts from a position to the end of the game, then take the average result as an estimate of how good that position was. This Monte Carlo idea, coupled with some heuristics and patterns, got programs up to strong amateur level. But they still couldn't topple pros without heavy handicaps. AlphaGo's key insight is, don't just search, learn how to think. If you look at the diagram in the paper's early pages, you see a pipeline of deep neural networks feeding into each other like stages of a factory. At the left is raw Go data, millions of human games. In the middle are powerful convolutional neural networks that interpret a board position almost like an image. At the right is a Monte Carlo tree search that uses these networks as a kind of intuition engine, guiding which branches to explore and how good they are likely to be. The first component is something called the Supervised Learning Policy Network, often written as P-sigma. Think of this as imitation AlphaGo. It's shown a position from a professional game, and its job is to predict the move that a human expert actually played. To feed a Go board into a neural network, the authors treat it like a stack of images. Each 19 by 19 intersection becomes a pixel. Around 48 different feature planes encode things like, is there a black stone here, a white stone, or is it empty? How many liberties does this chain have? How many turns ago was this stone played? Is a move here legal? Would it capture stones? Would it put your own stones into immediate Atari? The result is a rich tensor that describes not just the static picture, but some of the underlying tactical structure. This goes into a deep convolutional network, 13 layers of convolutions, with hundreds of filters each. If you've seen architectures for image classification, this will feel familiar. Convolution, ReLU, convolution, ReLU, again and again, gradually building up a hierarchy of local patterns into global understanding. At the end, instead of outputting cat or dog, the network outputs a probability for each possible move on the board. Training is simple in principle. Take 30 million positions from high-level human games, ask the network to predict the human move, and adjust the weights to increase the probability of the correct answer. On the test set, AlphaGo's policy network gets about 57% of moves exactly right. That may not sound amazing, but the previous best published results were around 44%, a large jump. And here's a subtle but important point. The authors show that tiny improvements in this prediction accuracy translate to huge differences in playing strength. In one chart, they plot the network's move prediction accuracy against its ELO rating when used inside AlphaGo's search, and you see a steep curve. Just a few percentage points of extra accuracy can add entire Dan ranks of strength. On another chart, they compare smaller networks with fewer filters to bigger ones. The bigger networks are slower, but, when search time is held constant, drastically stronger. However, there's a problem. Imitation only gets you so far. If you only train on human data, your system's ceiling is as good as your training set. Also, the objective, predict the human move, is not the same as win the game. Humans make mistakes. Pros occasionally choose beautiful, instructive moves rather than the most brutal winning move. The network needs to care about victory, not popularity. So step 2 in the pipeline is reinforcement learning, turning the supervised policy into a reinforcement learning policy network, PR. They start from the weights of the imitation net and let it play games against itself. No more human move labels. The only signal it gets is the final result of each game, win or loss. When the network chooses a move that ultimately contributes to a win, its parameters are nudged to increase the probability of that move in similar positions. When it loses, they're nudged the other way. This is implemented with a policy gradient method. Roughly, increase the log probability of moves that led to wins, decrease for those that led to losses, with some baselines to reduce variance. The authors also stabilize training by having the current network play against a pool of older versions of itself, so it doesn't overfit to a single opponent. The result? A network that no longer just imitates human style, but actively optimizes for winning. When tested head-to-head, this RL policy network beats the original supervised policy more than 80% of the time. And here's the crazy part. If you just let this RL policy choose moves directly, no search, no rollouts, just one forward pass per move, it beats the strongest open-source MCTS Go engine, Pachi, running 100,000 simulations per move, in about 85% of games. A single neural network, playing instinctive Go, is stronger than a handcrafted search program, burning CPU like crazy. But AlphaGo doesn't stop there. There's another piece, the value network, V-theta. The policy networks tell you, in this position, this is probably a good move. The value network answers a different question. From this position, if both sides play well according to our best policy, what's the probability that the current player will eventually win? It takes a full board position as input and outputs a single scalar between -1 and 1. Negative means likely loss, positive means likely win. Naively, you might try to train this value network on historical human games. For each position in a game, label it with the final result, win or loss, and train the network to predict that label. But positions within a single game are highly correlated. From move 150 to move 151, only one stone changes, but all those positions share the same final result. The network can just memorize patterns specific to individual games instead of learning general evaluative ability. Indeed, when they tried this, the value net overfit badly. So they do something clever. They create a massive self-play dataset specifically for value training. For each of 30 million games, they start from the SL policy and play randomly for a while. At a random step, inject a uniformly random valid move, something deliberately off distribution. From the resulting position, they let the strong RL policy network play both sides until the end of the game. They record just one position from that game along with the final winner. Each training example is therefore from a different game, and each label reflects the result of high-quality play from that point onward. This decorrelates the data and focuses the value net on the question, who wins from here if both sides are strong? On another chart in the paper, they compare the mean squared error of different evaluation methods: plain Monte Carlo rollouts with random policies, rollouts with more sophisticated policies, and the value network. The value network consistently predicts outcomes more accurately than doing 100 rollouts with a simple policy and approaches the performance of using the RL policy for rollouts, but with around 15,000 times less computation. So now AlphaGo has 3 powerful thought modules: a strong policy that imitates human professionals, a stronger, win-focused policy learned by reinforcement learning, a value estimator that predicts win probabilities from a position. The last step is to plug these into a Monte Carlo tree search in a really smart way. Imagine the search tree as a set of nodes, positions, and edges, moves. For each edge, SA, move A in position S, AlphaGo stores 3 key numbers: N of SA, the number of times this move has been visited in the search; Q of SA, the current estimated value of taking this move; and P of SA, a prior probability that this move is promising. At the start of each simulation, AlphaGo starts at the root, the current board position, and repeatedly chooses the move that maximizes Q of SA plus U of SA, where U of SA is an exploration bonus proportional to P of SA, but scaled down as N of SA grows. That P of SA comes from the supervised policy network. When the search first expands a node, it passes the position through P sigma and records its output probabilities as priors for all legal moves. This means the search is heavily biased towards moves that look strong to the policy net, but it still occasionally explores unexpected branches thanks to the exploration term. When a simulation reaches a leaf node, some position at the frontier of the current tree, AlphaGo does 2 evaluations. First, it calls the value network V theta on the leaf position to get a direct estimate of the win probability. Second, it launches a fast rollout. From that leaf, it plays out a complete game using the cheap rollout policy ppi, a lightweight pattern-based policy that can run thousands of playouts per second. Then it mixes these 2 numbers, value net prediction and rollout result, with a mixing parameter lambda, producing a combined leaf evaluation V of SL. This gets propagated back up the tree, updating Q of SA for all moves on the path and incrementing their visit counts. There are some sophisticated engineering tricks in the background. Multiple simulations run in parallel on different threads. To avoid redundant work when 2 threads hit the same node, AlphaGo uses virtual loss. Each thread temporarily pretends that path is slightly bad, pushing other threads to explore different branches. The policy and value networks are expensive, so evaluations are batched and run asynchronously on GPUs, while the tree search logic runs on CPUs. The tree itself is reused between moves. After AlphaGo chooses a move, that child node becomes the new root, and all its subtree statistics carry forward. There's even a distributed version. In the diagram on one of the later pages, the authors show a master machine doing the tree search, while dozens or hundreds of worker CPUs handle rollouts and worker GPUs handle neural network evaluations. One configuration uses 1,202 CPUs and 176 GPUs. This distributed AlphaGo, unsurprisingly, is even stronger than the single machine version. So how well does this whole system work? In an internal tournament, AlphaGo played against several of the strongest engines of the time: commercial programs like Crazy Stone and Zen, open source engines like Pachi and Fuego, and a more classical engine, GNU-Go. All programs got about 5 seconds per move. The single machine AlphaGo won 494 out of 495 games. That's a 99.8% win rate. In ELO terms, it was many Dan ranks stronger than the next best program. They also tried giving the other engines 4 handicap stones, 4 free moves at the start, a massive head start in Go. Even then, AlphaGo still crushed them, winning the majority of games. A bar chart in the paper shows just how lopsided the results are, with AlphaGo towering above the competition. The distributed version was stronger still, winning about 77% of games against the already dominant single machine AlphaGo. And then came the human test. From October 5th to 9th, 2015, AlphaGo played a formal match against Fan Hui, a professional 2-dan player and 3-time European Go champion. They played 5 official games with long time controls and 5 informal games with shorter time limits. AlphaGo won all 5 official games and 3 of the 5 informal ones. If you look at the game diagrams in the paper, you see the arcs of those battles. Black and white stones spreading across the board, clashes breaking out along the edges, thick frameworks turning into solid territory. In one figure, they dissect a particular position from an informal game. Several mini-boards show different statistics. One shows the value network's evaluation of each possible move. Another shows the action values from search. Another shows the raw policy network's preferences. And another shows how often each move was explored during simulations. You can see that the move AlphaGo actually played wasn't the single top suggestion of every component, but it was the move that the overall search, combining policy and value, considered strongest after thousands of simulations. Fan Hui later commented that in that exact position, AlphaGo's preferred move was in fact better than the move he played. All of this adds up to a striking conclusion. AlphaGo doesn't just crunch more numbers than humans, it thinks differently. Whereas Deep Blue famously evaluated hundreds of millions of positions per second in chess, AlphaGo evaluates thousands of times fewer positions in Go, but invests much more thought in each one. The policy network focuses the search on moves that look strategically promising. The value network lets it cut off search early with high-confidence evaluations, instead of rolling out all the way to the end. The Monte Carlo tree search stitches these elements together into a powerful look-ahead that feels, in many positions, eerily human. There's another important contrast. Deep Blue's evaluation function was meticulously crafted by human chess experts and engineers. It encoded decades of chess theory into thousands of if-then rules and hand-tuned parameters. AlphaGo's intuition is learned. The networks aren't handed high-level concepts like territory or influence explicitly. They infer them from millions of positions and outcomes. The only prior knowledge baked in is the rules of the game and the input features derived from those rules. That's what made this paper such a watershed moment. Go is the archetype of search plus intuition. For years, it stood as a symbol of what humans could do that computers couldn't. Long-term planning, reading out fantastically complex tactical sequences, and judging the beauty or ugliness of shapes on the board. By combining deep neural networks with search, AlphaGo showed that machines can, in some sense, learn their own version of intuition and plug it into powerful tree search algorithms. The techniques in this paper became the template for many later systems. Variants of policy and value networks, trained with self-play and combined with tree search, power not only later versions like AlphaGo 0 and AlphaZero, but also systems for planning, robotics, and complex decision-making problems far beyond games. And it all started here. A supervised policy that learned from human experts, a reinforcement learned policy that surpassed them, a value network that understood who was truly ahead, and a Monte Carlo tree search that knit all these components into something that felt like an alien Go genius. If you enjoyed this deep dive into the brain of AlphaGo, do me a favor. Hit like so more people see this, subscribe if you want more breakdowns of the AI papers that quietly reshaped our world, and drop a comment with the next paper you want to see turned into a story. Was it Transformers? GANs? AlphaZero? Your suggestion might be the next episode. Thanks for watching, and I'll see you in the next one.